Hi everyone, today we are talking about similar polygons. So just for a warm-up, we're asked to find the length of this model right here compared to the actual racing car, right? So to do that, we're going to set up a proportion. So first thing we see is that this racing car is 1.8 meters in, we can say, width, and then 5 meters in length. Okay, so I'm going to write a proportion stating that this is 1.8. Now my model is in centimeters, so I'm going to write this in centimeters. So this is 180 centimeters to 500 centimeters. Okay, and this is equal to, again here, my width is 6.3 centimeters, and my length is x. That's what I'm solving for. Okay, now I can do a simple cross multiply here. So what we're actually doing is multiplying both sides by each respective denominator, but I mean in actuality it comes to where we can just cross multiply. So we get 180x is equal to 3150. To solve for x, we divide, we get 17.5 centimeters. Okay, next question. Our class is making a rectangular poster. The design is 6 inches by 10 inches. Okay, the space allowed for the poster is 4 feet by 8 feet, so I'm going to have to dilate this. Okay, now what are the dimensions of the largest poster that will fit in this space? Okay, so the idea is I have some image which is 6 inches wide by 10 inches tall. Okay, but the space that I have is like this huge thing, right? Which is 4 feet by 8 feet, which in inches we will say is multiplying by 12, 48 feet wide, and then 96 inches tall. And so I would have to dilate my image, and I want to see how big of an image I can fit into this space. Alright, so to do that, I'm actually going to set up two different proportions. I'm going to set up one proportion, assuming that I've maxed out the width. Okay? Alright. And then I would find out what the corresponding height would be. Okay? The other way we can go about this is we can set up a proportion where we have maxed out the height, and we would solve for the corresponding width because the dimensions of my image are not going to change. Okay, so in this way we'll solve exactly how we did in part A. I would get x equaling to 80. Over here I would get x being 57.6 inches. We see here that our poster being 48 by 80 is going to be optimal, so the dimensions of the largest poster that will fit in the space are going to be 48 inches by 80 inches. And that's our final answer. Alright, moving on. A little bit of vocabulary. So, first of all, a ratio is what we use to compare two numbers by division. Okay, so the ratio of my two numbers a and b can be written as a to b, a colon b, or a divided by b, where b is not 0. Okay, so the ratios 1 to 2 can be written like this, literally. It can be written using a colon, it can be written using a fraction. They're all exactly the same thing. Okay, now within, I have an equation. Okay, now if I have an equation relating to ratios, that's what we call a proportion. Okay, now within this, the first and last numbers in my proportion are the extremes. Okay, they're like way out there, right? So they're the extremes. The middle two numbers are the means, so they're more in the middle. That makes sense. In this case, it really, when you're writing in fractional form, it doesn't really matter, but as much as when you're writing using your colons. But you could say that your extremes start on the left hand, the top, and then the right hand bottom, and then the means are the opposite of that. Okay. Now, in terms of my cross product property, again, the important thing to understand here is that you're not directly multiplying 2 by 6 and 4 by 3. What you're actually doing is you're multiplying both sides by 6, and you're canceling out the denominator here. And then you're multiplying both sides by 3, and you're canceling out the denominator here. Okay, that's really the important thing to know. But in practice, it ends up being where we just straight multiply our extremes and our means together. Okay. Now some other properties of proportions are as follows. So here, if we start with our proportion a to b is equal to c to d, okay, what I notice about my ratios is that a is also to c as b is to d. Okay, so what we see here is that there's a relationship across the equal sign. Okay, so if a to b is equal to c to d, that means a and c have a relationship, b and d have a relationship. They're also ratios. Okay. Now in this case, a is to b as c is to d. That would also mean that b is to a as d is to c. So the reciprocals will also be true. Okay, now here a is to b as c is to d, and that means that d is to b as c is to a. So the way that we could think about this is, in actuality what we did is we switched our extremes, okay, but you could also think about this as, if I have a over b is equal to c over d, what if I multiplied both sides by d? And then I also multiply both sides by 1 over a. Okay, and then I would end up with d over b is equal to c over a. Okay, so it's just another way of writing this. We manipulated it a little bit mathematically. Okay, and then last one is if I add the denominator again to the top, it doesn't actually change the proportion. Okay, so it doesn't really matter. The ratios will remain intact. Okay, so let's practice using our properties here. With these four, let's practice each of the four properties that we just talked about. Okay, so first I have 2/3 is equal to 4/6, which is true. Hey, what this means is I can rewrite these as a ratio of 2 to 4 and 3 to 6, which is also true. All right. Next one. So I have 2 to 3 is equal to 4 to 6 again. That means that the flip of each of these is also going to be true. All right. So we just take the reciprocal, set them equal to each other for our proportion. All right. So same thing that we did over here. So if I flip my extremes, or what I actually did in practice is I multiplied. Okay. But if I flip my extremes, we also get a true proportion. All right. And then last but not least, if I add my denominators to both sides, I do not end up changing anything. So I end up with 5/3 is equal to 10/6, which is also true. Alright, let's move on. What's happening here? Alright. Okay, so a little bit of vocabulary and then some examples. So we say that figures that are similar, which we use a tilde to represent that, have the same shape but not necessarily the same size. So we say that two polygons are similar if and only if their corresponding angles are congruent and their corresponding side lengths are proportional. Right, so that's the important part. Their angles must be congruent. Their angles have to be the same. Their side lengths are proportional. That's the difference between similarity and congruence. Alright, so in our first example, if triangle MNP is similar to triangle SRT, then what are the pairs of congruent angles? So the way that I typically go about this is I look for something that sticks out. In this case, I see that I have an obtuse angle on M, I have an obtuse angle on S, and then I'm going to pick everything else relative to that. Okay, so I see that R is up here, so that means N, and then T and P will also be congruent. So let's write that out. I see that angle S is congruent. Let's do it better. Is congruent, that's barely better, to angle M. Angle R is congruent to angle N. And angle P is congruent to angle T. Okay, they want to know the extended proportion for the ratios of the sides. Okay, so I'm just relating the sides here. I know that MN is to SR as MP is to ST as NP is to RT. So again, you're just looking at the sides and using the same angles as a point of reference. Okay, now a similarity ratio is the ratio of the lengths of the corresponding sides of two similar polygons. Okay, so the similarity ratio of triangle ABC, which is given here, to EDF, we would say is 1 to 2, right? Because each side length is 1/2. So I could say 1 to 2 or 1/2. Okay. Now the similarity ratio of DEF to ABC is the opposite. So I see that DEF, the side lengths are 2 times greater than the side lengths of ABC. So we would say that the similarity ratio is 2 to 1. Alright, let's do some more examples. So we want to determine if these rectangles are similar, and then if they are, I want to write a similarity statement, give the scale factor. Okay, so what I need to do is compare the side lengths and see if my side length AB and side length EF can create a true proportion with side lengths AD and EH. Okay, so I'm going to compare AB to EF, and this must be true in regards to AD and EH. Okay, so if I fill in the numbers here, AB is 6, EF is 4, AD is 9, EH is 6. So I do see that this is true. This does create a true proportion, and so these triangles are similar. The way that I would talk about that is that quadrilateral ABCD is similar to quadrilateral EFGH. Okay, and in this case, the scale factor is going to be 3/2. The scale factor is 3/2. So if we just simplify right here, we end up getting our scale factor. Okay, next example, we want to determine if these triangles are similar, and if so, write the similarity statement. Okay, so it looks like I have two isosceles triangles. So if I find my angle here, I just have to subtract 36 from 180, so I get 144 divided by 2 is 72. So right off the bat I see a problem. I see that my angle QPR is not congruent to angle TSW. So because my angles are not congruent, these triangles cannot be similar. So they're not similar triangles, and I'm going to move on. Okay, this time they tell us that our triangles are similar. They want us to solve for the variable and for the missing side. Okay, so I'm going to create a proportion. I see that RM and DG are our kind of related sides, so I'm going to write a ratio. 6x minus 7 is to 49, and then from here we have options. So you could pick AM to OG or AR to OD. I'm going to pick AM to OG. So it's 25 to 35. Okay. So solving this out, we can cross multiply. I end up getting, let's see, 210x is equal to 1470. And if we solve for x, we get 7. Alright, now so I'm going to plug 7 in for x. I get 42 minus 7, which is 35. Right. Okay, and last one, I have two trapezoids, and they want us to find x and y respectively. So I need to create a proportion. So let's set up some ratios here. One ratio is that x relates to 7.5. So x is to 7.5, as it looks like y is to 5, and it looks like 6 is to 9. Right, so it looks like my scale factor here, my ratio is going to be 2/3. Right. So given that, we can solve our proportion here. So if we just isolate, x is 7.5 is to 6/9, y over 5 is to 6/9, then again we can do that. So we can solve. So x is to 7.5 as 6 is to 9. That would give me that x is 5 Okay, then y over 5 is 2 6 over 9, so then y is equal to 10/3. Alright. And the last one is the space allowed for mascot. So very similar question as to our warm-up. Okay, now I would want you to try this, but you'll end up finding that once you set your proportion, this time we are starting with a larger image, and then we are dilating down, right? So we're shrinking to fit a smaller space. So I have a proportion here. So 500 is to 375, as, again, we would probably try to figure out the largest space that we can occupy, but we end up finding out that actually this fits perfectly. Right, 500 over 375 is to 120 over 90. So 120 over 90 is actually going to be the largest image that our mascot will fit on this web page. Alright, so your homework is not this. Your homework is a separate worksheet on Google Classroom. So if you have any questions, let me know. Otherwise, have a fantastic rest of your day.